Hello, my name is Aiden Paradis, and this is Lab 4 with circuits. So to introduce this lab uses an AC circuit simulation software to simulate how circuits work in the real world. We're going to use this simulation to show how the relationships of like energy and current conservation work in multiple types of circuits. This lab is very beneficial to us because it provides multiple components, or it provides basic practice with multiple components of circuits such as capacitors, resistors, and voltmeters. So here we have a series circuit uh, with two batteries, 1.2 or 1.5 volts each, so it adds up to 3 volts. We have two resistors as well, and this is my graph on the right. As a charge flows through the batteries, we get the EMF to go up to 3 volts, and then it goes through the first resistor, which has a resistance of 47 ohms, and then goes to the second resistor, which has a resistance of 100 ohms, and ultimately goes back to 0 because we know that once you get back to the batteries, the change in the voltage is 0. And that can be represented in the graph here. So here's the calculated values. For this experiment, we assumed that the resistance of the wire and ammeter are 0, which is not true in real life. The resistance calculated was 0.02 amps. Resistance of both of the resistors, respectively, were 50.1 ohms and 99.9 ohms. And right here you can see the equation used to calculate the resistance of each of these resistors. This was an RC circuit. So the way this works is as the electrons flow, the capacitor gets charged by the equation Q over C, and the resistor will, or I guess the bulb in this case, will start out really bright and then dim as the capacitor absorbs more charge. And this can be shown by this equation here. Actually, no, sorry. This equation here is for when you disconnect the battery and the charges flow the opposite direction. The capacitor will begin to decrease in charge, and the light bulb will start to increase in luminescence. And this is the voltage relationship, delta V equals 0 throughout the thing, or throughout the loop, I'm sorry. QC is the capacitor, as can be seen here, and IR is the resistor. So here's my data. You can take a look at this. I don't know if I really need to actually read this to you guys. You can just look at it yourself. But these were all calculated using this equation and altering the equation. The graph values, my Excel graph did not turn out the way I wanted it to, so I just did the calculations kind of by hand. The theoretical value is 30 times 0.2. I'm sorry, because the resistance was 0.2. Yeah, that should be 0.2. And 30 volts was calculated. And then my experimental value using the natural log of delta V over delta V naught ended up being 0.05 seconds, which is very close to the theoretical value. Some questions to ask about this experiment. If we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter, what's different about a real ammeter and how would have it affected the circuits you hooked it up to? So for this experiment, we assumed that the ammeter had 0 resistance and that the wire had 0 resistance as well. So we would have to add the resistance of the actual ammeter to the equation, and the resistance of each individual resistor would decrease a little bit because we add a little bit of resistance to the equation. And then if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. So if we had a real battery, obviously this simulation slowed down time like very quickly. In real life, the charges move at light speed, so the time would be much, much, much slower. So our ideal model would predict the capacitor to reach full charge in a very, very short amount of time, milliseconds. And I think that answers all the questions we need, and that's the end of my presentation. Thank you.